There are very many types of reactions, like very many, like a lot. So many that it would be silly to try to focus on them all in a general course like this one. You'll see 11 million individual organic reactions between Orgo 1 and Orgo 2. And you'll see an army's worth of reactions in your biochem courses. They'll even sneak into your biology courses. So there's not a great reason for us to cover all of them here. Instead, we're going to focus on two pretty big and general groups of reactions: double displacement reactions and single displacement reactions. We will see specifics of both of these types of reactions later in this section. Our goal here is to be able to recognize them and see how the building blocks of these compounds move in each of these cases. I truly hope that you have looked forward to reviewing a number of beautiful colored dots these very many days we've been together this term, because if so, you are in luck. This is a many colored dots kind of topic. Now here's your first set. These colored dots represent a double displacement process. Now these puppies are more than just pretty colors. They're representing the building blocks of this double displacement reaction, specifically the positive and negative portions of dissociating compounds. These are usually going to be ionic compounds and acids for our purposes in this class. Now this brings us to the first key point regarding double displacement reactions. The reactants are always two species that can dissociate into a positive and negative portion. And the products are always two species that are formed from that dissociation. That formation is due to a switching of ion partners. The chemist might think of both of the anions displacing each other to pair up with the opposite cations, or both of the cations displacing each other to pair up with the opposite anions. Two things are being displaced, so double displacement reaction. But it might be more simple to just say that a double displacement reaction involves a swapping of ion partners. Now that was a lot of words, so let's look at what actually happens in a double displacement reaction. Now the chemist is going to begin with aqueous solutions of their salt or acid. So we saw in the last subsection that AQ means that instead of an intact salt like what I have here, we actually have multiple cations and multiple anions that are going to be floating around in our reaction mixture. Because opposite charges attract, once separated like this, cations and anions are free to pair up any way they see fit. If a new cation and anion pair is formed, we end up with a double displacement reaction. Some notes to make. Now first, for our purposes, both of the reactants here are going to be soluble in water and therefore will dissociate into ions as I have shown. Now that doesn't actually have to be true in real life, but it simplifies our course life. So both reactants will be aqueous solutions of soluble salts, and there's more on that in section 2.2. Now second, and again, this is for our purposes versus in real life, your products will either both be aqueous compounds that can dissociate into ions, or you will only have one aqueous compound and the second will be a solid, liquid, or gas. With the exception of our gas formation reaction, which we'll see in section 2.3, and potentially a homework problem here and there, you will never, ever, ever, never have two compounds that aren't aqueous on the product side of a double displacement reaction. Think quizzes, etc. for this course. Now this will become important in the next sections as we identify our products and we give them states of matter such as solid, liquid, or gas. Now third, there are parts to this 3 here. If you have products and they're ionic compounds, you have to follow all of the rules you already know about ionic compounds. Cations will only pair with anions. The cation has to come first in the new formula and the anion has to come second. The new compounds have to be neutral overall. You'll need to use parentheses if you need more than one polyatomic ion in a compound. All of the things you learned about ionic compounds are still true here. This is one of the things that makes precipitation and double displacement in general pretty difficult. Lastly, it will be very important to remember that nothing changes oxidation state or charge in a double displacement reaction. Meaning, if copper was present as a 2+ cation on the reactant side, it's going to have to be present as a 2+ cation on the product side. It can't change oxidation state to the 1+ cation between the two sides. This fact helps when trying to determine the formulas for the products. Now, you shouldn't be concerned if you can't predict your products right now. That's the goal of later sections in this module. Right now, what you're aiming to master is realizing that if a reaction contains 4 different ion pairs, that reaction is likely a double displacement reaction of some sort. The second big reaction type is a single displacement reaction. And you guessed it, only one thing is going to get displaced here. Now, before we define this any further, you can ID a single displacement reaction because the reactants will always be an element, shown with an E here, and a compound, shown as a cation-anion pair. Your products are a new element and a new compound. Both of the elements involved are going to be neutral. They will have an oxidation state of 0, meaning they don't have a charge, because they are elements. The compound overall will also be neutral, but will be composed of positive and negative portions. Since there is only one thing that gets displaced, this seems like it should be easier than the double displacement reactions, right? Well, not really, because we can't just willy-nilly switch partners here, and here's why. This example, which is the one from the last slide, is an example of a cation displacement reaction. I know this because the reactant element is positioned as a cation in the product compound. This means that the reactant element is something that tends to form a cation, usually a metal or a molecule of hydrogen. Once it forms a cation, it will seek out other anions, and the only one that can be found is currently paired with a different cation. So the newly formed cation has to displace that old cation with nothing else to do. That displaced cation goes, gains some electrons, and forms a new element. We'll go over all of that again in section 2.4. Now the orange circle was an element on the reactant side and was therefore neutral, had a 0 oxidation state. When it displaced the cation, it had to lose electrons and become a cation itself to do so. So the orange circle changed oxidation state or charge. When the blue cation became displaced, it gained the electrons that the orange circle lost and became a neutral element. It also changed oxidation states. In addition to only one thing being displaced, the second big difference between a double and a single displacement reaction is that the latter will involve change in oxidation state, technically 2. This makes them fundamentally different, so you will need to be sure to include single or double and not just displacement reaction when you identify these. Now that's a lot of specifics. Your focus right now is first recognizing that this is a single displacement reaction because of the element compound pairs found on both sides of that reaction arrow. And second, recognizing that this is a cation displacement reaction because the reactant cation looks like it has been displaced. If there is a cation displacement reaction, you might have guessed that there's also an anion displacement reaction. Now there are fewer of these, which makes sense because we learned that the majority of our periodic table is prone to forming cations. In an anion displacement reaction, the reactant element is something that tends to form anions. Think the nonmetal elements such as halogens, nitrogen, and oxygen. The other reactant in an anion displacement reaction is still just a compound, just a cation-anion pair. The difference between the two single displacement reaction comes when the displacement itself actually occurs. Since your reactant element will be prone to forming anions, the anion in the reactant compound will now be displaced. The displaced anion will form a new element. Now, be careful here because there are often diatomic elements and these will require a subscript of 2. So again, your focus right now is realizing that this is a single displacement reaction that starts very similarly to the cation displacement reaction. The characteristic element compound pairs are again found on both sides of the reaction arrow. This is specifically an anion displacement reaction because the reactant anion has been displaced by the reactant element. We will elaborate on single displacement reactions in section 2.4.